What happens when you give a foundation model a video game controller, a live camera feed, and absolutely no prior knowledge of the game? It stalls. It loops. It forgets how to fight. For embodied agents, long-horizon partial observability has been the ultimate bottleneck. But a new paper from Princeton, Arise, and Google DeepMind shows how to break that bottleneck, not by hard-coding more tools, but by letting the agent continuously rewrite its own scaffolding while it plays. Right now, agentic harnesses are standard infrastructure for coding. Tools like Claude Code or OpenHands wrap a foundation model with memory, planning, and specialized tools, letting it navigate codebases across thousands of steps. But for embodied agents, we are still largely relying on hand-engineered scaffolding or resetting the environment after every failed attempt. The PokeAgent challenge proved that without domain-specific scaffolding, even frontier vision language models make almost zero progress on RPG gameplay. The core problem isn't just reasoning, it's that the agent's context and tooling can't adapt to failures it hasn't seen yet. The solution is called Continual Harness. Instead of a static prompt or a reset-based optimization loop, it treats the entire agent setup as a living state that evolves mid-episode. You start with a brutally minimal interface, a rendered frame, a local ASCII text map of the visible area, and a fixed set of button inputs. From there, the harness decomposes into 4 components: a system prompt for strategic guidance, sub-agents for specialized tasks, a skill library for reusable routines, and a memory tree for persistent knowledge. The agent acts, the environment updates, and a trajectory accumulates. Here is where the architecture gets interesting. Every F steps, after a brief warm-up period of W steps, a separate refiner model steps in. It reads the recent trajectory window, scans for failure signatures like navigation loops, tool call crashes, or stalled objectives, and then runs 4 targeted passes. First, it rewrites the system prompt to correct strategic drift. Second, it manages subagents by creating new ones for repeated multi-step patterns, editing existing ones to patch failures, and deleting dead weight. Third, it codifies successful action sequences into executable skills and patches broken code. Fourth, it updates memory, adding fresh facts, demoting outdated ones, and filling strategic gaps. Crucially, all of this happens through a fixed set of meta tools like define agent, run code, and process memory. The harness state updates in place, and the agent continues playing without a single environment reset. This reset-free architecture isn't just a convenience, it fundamentally changes what the agent can learn. Reset-based prompt optimization methods, like GEPA, require running complete episodes, evaluating them, and starting over. That destroys long-horizon context. Continual Harness accumulates failure signatures monotonically. A mistake made early in the run remains part of the refinement context for later stages. This means the agent can solve problems that only emerge deep in a playthrough, like late-game boss mechanics or complex multi-step puzzles, which reset-based methods literally cannot reach by construction. When tested on Pokémon Red and Emerald, this approach drastically cuts down the button press cost compared to a minimalist baseline. Across Gemini 3 variants, it recovers the majority of the efficiency gap to a hand-engineered expert harness, all while starting from zero curated knowledge. But here is a critical technical finding: the gains are strictly capability dependent. On Gemini Pro, the harness is strictly Pareto dominant, slashing costs by 40% without sacrificing completion. On Flash, you see high variance. And on Flashlight, the system actually underperforms the baseline. This reveals a clear capability flaw. The refinement loop requires a base model that can sufficiently parse and utilize the evolving harness components. Below that threshold, in-context adaptation stalls. The framework doesn't stop at inference. It closes the loop with an online co-learning pipeline that trains open-source models using the same self-improving harness. After a warm-up phase, each training iteration runs a fixed-length rollout through the live refining harness. A pairwise process reward model scores every transition, focusing on trajectory progress, action correctness, and reasoning quality. Low-reward windows are then relabeled by a frontier teacher model, and the open-source model, like Gemma 4, is updated via soft supervised fine-tuning on that relabeled shard. The emulator state persists across iterations. The model's in-game position doesn't reset, it compounds. The results show sustained milestone progression across training steps, proving that the trajectory distribution the model learns from co-adapts with its own policy. Continual Harness formalizes a pattern we have seen emerge in human-supervised agent runs. The most capable models naturally start iterating on their own strategies when given the right meta tools and persistent memory. By automating that loop and making it reset-free, this framework bridges the gap between static prompt engineering and dynamic, embodied reasoning. It is a significant step toward foundation agents that do not just execute plans, but continuously rewrite their own playbooks in real time. If you want to dive into the full methodology, ablation studies, and the open-source co-learning setup, the paper is linked below. I will see you in the next one.